Okay, good morning, everyone. So welcome to this session. And in this morning session, we will have two local speakers. So our first speaker is Professor Das. He's from BIMSA, and he's going to talk about Bayesian quantile joint modeling of multivariate longitudinal and time-to-event data. Let us welcome him.
Thank you. So, good morning everyone. As you can see, the title of my talk is a Bayesian quantile joint modeling of multivariate longitudinal and time to event data. So, it is a data driven statistical method. That means the problem comes from a given data set, although the problem is a more general problem, but it comes from a particular data set, and then that particular data set motivates us to develop some statistical method which is appropriate for handling not only this particular data, but this type of data in general. So, this is the brief outline of my talk. I will start with the motivating data, and then I will discuss the proposed Bayesian quantile joint modeling. So, there are three different parts of it: joint modeling, quantile joint modeling, and Bayesian quantile joint modeling. Then I will discuss the results, followed by some simulation study and summary. So, to give you the brief outline of this talk, the motivations of this problem is acute lymphocytic leukemia, which is possibly the most common type of cancer among children. This is also known as acute lymphoblastic leukemia. This is a blood cancer, and this happens when you have immature white blood cell. It is well known from the previous study that this acute lymphocytic leukemia is not a genetic disease. It is not exactly inherited from the parents. However, it happens due to mutations in the DNA that has been already reported in the literature. Over the years, people have developed multi-drug chemotherapy, and because of that, the survival rate, that means the people don't die from this thing, they eventually survive. The survival rate has increased significantly in the last 20 years. To the latest news in 2018, well, this might not be the latest one, but globally more than 876,000 confirmed cases of leukemia was noted, and that resulted in a death of 110,000. Okay. As I mentioned, because of this advanced chemotherapy, the survival rate of acute lymphocytic leukemia has increased from 10% to 90%. In the year 1960, it was 10%. In 2010, it is 90%. But unfortunately, that is only for the developed countries or the first world countries like the United States. And this success of the maintenance therapy is mainly due to the longer program where the children are treated for the first 2 years. They are given some medicines for the first 2 years, and then they are followed for the next 3 years. However, the picture is not the same for the Asian or the African countries. It is reported that the survival rate is below 60% in the African countries and below 70% in most of the Asian countries. So, based on that, we consider a particular clinical trial data set. So, Tata Translational Cancer Research Center, it is a well-known research institute in India. They conducted a chemotherapy clinical trial with 236 children who were detected as the leukemia patient. So, this was a 5-year study, started in 2014 and ended in 2019. As I said, the part of this program is for the first 2 years, the patients are treated, and once the treatment is over, they are followed for the next 3 years just to see whether there is any side effect of the treatment or if there is a relapse due to the treatment. The patients were treated with 2 standard drugs, very standard drugs, which is known as the textbook drugs in some sense, 6-MP and MTX. and the median duration of the treatment was 92 weeks, almost 2 years. Children belonged to the age interval 1 to 17.5 with a median age of 4.7 years. That means most of them were very, very young kids, and 36% of them were female. So this is the motivating data set. So what happens once the patients come to the clinic and they are detected as the leukemia patient? Based on the white blood cell count, patients are prescribed different dose of the drugs. 2 different drugs as I mentioned, 6-MP and MTX. But what dose should be prescribed, that depends on the initial white blood cell count for these children. And after that, those children are asked to visit the clinic either weekly or bi-weekly or once in a month, depending on the severity of the disease. And every time they visit the clinic, 3 important biomarkers are measured: lymphocyte count, absolute neutrophil count, which we denote by ANC, and platelet count. So these are the 3 important measurements that are taken from each patient every time they visit the clinic. The median number of visits was 41, and the children did not join the study at the same time. That means all the patients did not come to the clinic at the same time, and all the children, they do not visit the clinic every week or every other week. So because of that, the resulting data set is an irregular multivariate longitudinal data. It is longitudinal because you are getting repeated measurements from each children. It's multivariate because you are getting 3 measurements: lymphocyte count, neutrophil count, and platelet count at each time point. And it's irregular because the interval and the number of visits are different for different child. Okay, once the treatment is over, those children are followed for the next 3 years, approximately next 3 years. If there is a relapse, then that time is noted. If there is no relapse, then those children are censored at the time point where the study ends, because you cannot follow them for an infinite period. So you have the follow-up period almost 3 years, and if you observe there is a relapse for some child, you will note the time of the relapse, otherwise the child is censored at the time. Alright. So for this type of data, drug doses are the time varying covariates, because the dose of the drug change from time to time for the patients. So those are the time varying covariates. And there is a long list of time invariant covariates, which are measured only at the first time point, most of the cases, like the age of the child, gender, lineage, and something else. Okay. So this is basically the motivating data set. And based on this data, first we perform some exploratory data analysis before we understand what type of model is appropriate. And by the way, the goal of this study is to find out the effect of the medicine, the 2 medicines that we are giving, 6-MP and MTX, how this drug work on the children. Okay. So what should be the optimal dose that should be prescribed for a child if I want to reduce the lymphocyte count, which is the most important measurement, and if I want to delay the relapse time, that means I just want to make sure that the patients survive. Okay. So first we do some exploratory data analysis. What we do here, this is just 4 randomly selected child, and the solid curves are for the children for which we got a relapse, and the dotted curves are for them for which we did not get a relapse. We have 3 plots, one for the lymphocyte count, neutrophil count, and platelet count. This solid horizontal line is the mean value, the mean curve, that we are getting. This is standard. So all the children we have, we calculate their mean. And what we observe that the children for which we got a relapse, they more or less had a higher lymphocyte count than the median. And they had, on the average, lower neutrophil count and lower platelet counts. On the other hand, the children for which we observed no relapse, they maintained a lower lymphocyte count and a higher neutrophil and higher platelet count over the time period. So this particular plot reflects that something is happening with the relapse and the lymphocyte count, neutrophil count and platelet count. So these three important biomarkers somehow have some effect on your relapse. Whether you will observe a relapse or not, that is possibly controlled by these three biomarkers. Just an impression. Next we make a contour plot. As you might know, contour plot basically tells you the density, data density at different parts of the distribution. So although we have three biomarkers, but we are just making a two-dimensional plot. Along the x-axis we plot the log neutrophil count, and here we are making the log platelet count. So for different levels of the density, each color indicates one particular density level, and for each color we have a dotted curve, we have a solid curve. Again, solid curve for the children for which we observed the relapse, dotted curve for them for which we had no relapse. We note that in the central part, that means at the median level, both the curves are more or less similar, and we cannot say that one is higher than the other. But once we move towards this green arrow or along this arrow, we see that the dotted curve dominates the corresponding solid curve. You see, this dotted curve dominates this solid curve. This dotted curve dominates the solid curve. That basically means that once you move to the higher quantile level for neutrophil and platelet count, you have a less chance of relapse. On the other hand, if you move along this arrow or that arrow, you see that the solid curve dominates the corresponding dotted curve. That means if you move to the lower quantile level, then you have a higher chance or higher probability of relapse. So this particular plot indicates that not only your relapse is related to those biomarkers, but they depend on different quantile levels also. So you really cannot model it at the mean level or the median level, because in the median level there is really nothing interesting. But more you move towards the higher or the lower quantile level, something interesting happens. So this motivates us to develop a quantile regression model. And quantile regression model, as you might know, on the contrary to the traditional mean regression model, where our focus is to find out the effects of the covariates on the mean of the response, in the quantile regression, we model the conditional quantile of the response, conditional on the covariate, and we really try to predict the quantile levels of the response variable, based on which we can find out the underlying probability distribution. Okay. So these two plots basically indicates that we should possibly develop a joint model because first we have to model the evolution process of the biomarkers using some stochastic model, and then the relapse time should be modeled with respect to these biomarkers. This plot indicates that you should model this thing at different quantile levels and not just at the median level or the mean level. So based on that, we develop a quantile joint model, and Bayesian approach we prefer because of the computational simplicity, which I am going to discuss now. So what is the goal of this research now? With the goal of quantile specific inference, we have three questions that we want to answer. First, we want to identify the biomarkers which are associated with the relapse time. That means these three important biomarkers, how they are related to the time to event, that means time to relapse at different quantile level. Detecting the time invariant covariates with significant effects on the biomarkers and on the relapse time, and to find out the effect of the drug, two important drugs that we are giving, what is the effect of the drugs on the longitudinal biomarkers. So again we have two different things. First, we are modeling the longitudinal trajectory, the evolution of the biomarker, and then we are modeling the time to event, that means time to relapse, as a function of the biomarkers and the time invariant covariates. Here is our notation. So Yijk. Okay, first we make a log transformation because that stabilizes the variance. As you can see in this plot, the values are very large, especially for the platelets, and these are count. So a log transformation is needed for the variance stabilization. So Yijk is the log transformed kth biomarker from the ith patient at time Tij. This j equals to 1 to tau I. This takes care of the fact that different individuals are measured at different time points. That means you have an irregular setting. So for every individual, you either observe the relapse time Ti when the cancer returns, or you observe the censoring time when that child stops coming to the clinic, because you cannot follow the individual for a long time. So either you observe a relapse time or you observe the censoring time, and if the relapse time is smaller than the censoring time, then this is basically a case of relapse. Otherwise, this is just censor. So we define small si as the minimum of Ti and Ci, and this is the time of interest for the ith patient. Okay, this is our time to event. All right. So what is the main contribution of our work? Typically, when we have the multivariate quantile regression modeling in the literature, they focus on a particular quantile level and they fix that level for each responses. That means if I have 3 response and I fixed a quantile level, then they model the quantile level for each response at the same time point. What we are doing, we are making a little bit flexible setup. We are defining the vector tau as tau 1, tau 2, tau 3 as if we can consider different quantile level for different responses simultaneously. So if I have 3 biomarkers, as I said, I might have patient who had a higher value of the lymphocyte but a lower value of the neutrophil and a median value of the platelet. Or I can have the patients for which I have a lower value of the lymphocyte but a higher value of this and that. So it doesn't mean that all the responses have to be modeled at the same quantile level. Okay? I might have the flexibility of modeling different responses at different quantile levels. So this is my vector tau, and what we model, we are using the standard quantile regression model. So this is my response. There is a effect of time. This is the function of time. This is the effect of the time varying covariates, which is the drug in this case. This is the effect of the time invariant covariates Zi. This is the subject specific random component, which basically takes care of the longitudinal dependence and the correlation among the biomarkers, and this is the random error. So in this model, this is the linear mixed model, and the effect of time, this can be modeled in many different ways. Either you can use a polynomial function or you can use some more sophisticated approach like B-spline, wavelets or anything like that. Here we are just using the polynomial function of time, and the orders of the polynomials can be get from AIC-BIC. This random component is another extremely important thing in the linear mixed model. In the traditional literature, people use subject specific random intercept and random slope. But the limitation of this thing is that in that case you are basically assuming that the random effects, subject specific random effects are linear. We are making it more flexible in the sense that we are modeling it by multivariate Brownian motion that has been already proposed in the context of linear mixed model. And this is more flexible because it doesn't assume any specific functional form and it can just model it in a more flexible way. All right. In addition, whenever you are doing the Bayesian quantile regression model, in the typical linear regression model, we assume that these random errors are IID normal with mean 0 variance sigma square. Because of that, expectation of YI becomes this part. But we are now modeling quantile. So in the quantile regression, Bayesian quantile regression, what we want to make sure is that this particular part becomes the taueth quantile of the response, and that can be obtained by assuming that this error part, random error, follows asymmetric Laplace distribution with location parameter 0, scale parameter sigma k, skewness parameter tau k. This has already been proposed in the literature long time back, Yu and Moit 2001, Gerasi and Bottai 2007, and many other people. So what they do, they assume a asymmetric Laplace distribution, appropriately such that this particular part becomes the conditional quantile of the response. Okay, we are just doing the same thing. However, for the computational simplicity, since we are using Bayesian method, we need to do Bayesian computation. We exploit the mixture representation of asymmetric Laplace distribution. An asymmetric Laplace distribution, if epsilon I j k follows asymmetric Laplace distribution, you can write that as a mixture of two distribution Eijk and Vijk, where Eijk's are exponential and Vijk's are standard normal, and theta 1 and theta 2 has some specific form. That means conditional on Eijk, epsilon ijk follows some normal distribution. That makes the computation super simple. A specific case of that was proposed by Park and Casella in 2008 in their famous Bayesian lasso paper, where they consider a symmetric Laplace distribution, symmetric Laplace because it is symmetric about mean 0 and median 0, and what they did, they again used this similar type of representation in the context of a symmetric Laplace distribution. Okay. So, conditional on the subject specific random effects and Eijk, with this representation my response will follow a normal distribution, and that makes the computation very simple. So, this is the first part. This part we are just modeling the longitudinal trajectory of the 3 biomarkers. You can have as many biomarkers as you want, but this is basically modeling the evolution of the longitudinal process. You are observing the patients for 2 years. So, first you model with your medicine how your longitudinal curve for the biomarkers change, and you can measure the effect of your medicine from these estimates. Second part, you consider time to event model, because you want to model the time to relapse, how early you can obtain a relapse or whether the relapse is delayed. For that we consider the traditional semi-parametric Cox proportional hazard model, but again at the quantile level. So, what we are doing, we are assuming that the hazard, so this is the quantile specific hazard, hazard means the instantaneous failure, it is the semi-parametric Cox proportional hazard model. So, there is a baseline hazard, and then you have this part where first part is the longitudinal trajectory of the biomarkers which you get from this model. So, you are basically incorporating this model here as a predictor, and then you consider the effect of the fixed covariate. So, your hazard function depends on the evolutions of the longitudinal biomarkers and the time invariant covariates. This model implicitly assumes that the medicines that you are prescribing for the patient has no direct effect on the relapse time, which is intuitive, because medicines when you take, medicine does not decide whether you will survive or not. Medicines actually control some of the features of your body, biomarker, and those biomarkers have the direct effect on the time to relapse. So, this is the implicit assumptions of this model, which is very standard. So, as I say, this particular parameter psi, it measures the associations of the biomarkers with the time to event, and we really need to test statistically whether these parameters are significant or not, because these parameters, these coefficients actually indicate how these biomarkers and the time to event are associated. For modeling the baseline hazard, again we can use many different ways, but we follow the approach suggested by Rizopoulos in 2016, where he was just using the B-spline and he was just taking a large number of knots, and for each of these coefficient he was considering some shrinkage prior, lasso type shrinkage or local global shrinkage. So, based on that, as I mentioned, so with our mixture representation, with this mixture representation for Yijk conditional on E and W, we can get a simple normal distribution, and that makes our life easy because you can write down the joint likelihood, and for the survival part also based on the hazard function you can get the corresponding likelihood. So, this is basically my joint model because it simultaneously models Yijk as well as the time to event, and everything is just inbuilt in this model. So, this is my joint likelihood for the joint model. Now, based on this likelihood, we are following the Bayesian approach And as always in the Bayesian approach, we consider some prior distribution, some prior distributions for the model parameter. So my capital theta is the set of all model parameters, both from the longitudinal model and the time to event model. And the posterior distribution is actually proportional to the joint likelihood times the joint prior distribution. Okay. So this is my joint posterior, and assuming the independent prior distributions for different parameters, this joint prior is basically the product of the individual prior. And of course, as you can see, this model is quite complicated because it has many different parts. Again, the priors are complicated, so the whole posterior is very complicated and you cannot directly sample from the posterior. So we exploit the very well known Markov chain Monte Carlo algorithm, which considers the joint posterior distribution, computes each of the full conditional distribution and keeps sampling from the full conditional distributions. And at the end of the day, once you have the samples from these full conditionals, you ignore the things that you don't need and only focus on the parameters you want to estimate. So whenever you are running this Markov chain Monte Carlo algorithm, we basically consider 50,000 iterations, and the first 2,000 values are rejected or discarded as burn-in to remove the effect of the initial values. And once you have the remaining values, which is almost 48,000 values, you basically consider the sample mean to estimate the underlying model parameters. Very standard approach. So you run the chain 50,000 times, remove the first 2,000 iteration, and whatever the remaining values you have, you consider the sample mean of these iterations and estimate the corresponding parameter. So this computation, it seems complicated, but fortunately after 2018 we have something called JAGS. JAGS stands for just another Gibbs sampling. So this JAGS is inbuilt in R, and it can perform this Monte Carlo algorithm for the complex model. So all our computations are performed in R JAGS. Standard convergence checks and posterior predictive checks are done. So once you use Markov chain Monte Carlo, you cannot just take the sample mean, you have to first make sure that you have the convergence of the chain. And for assessing the convergence, we have some standard techniques. So this is the plot. We make the trace density plot and the posterior plot. This trace plots indicates I have a very nice convergence, because if you have a convergence, that means the values basically fluctuate with some central values or mean values, that you can see for almost all coefficients is basically showing that you have a very nice convergence. And then these are the estimated posterior density plots for the different parameters, which are almost close to the normal, so it makes the things simple. So before we move, we have to now ensure that the joint model is actually appropriate for this type of data. You can also do the separate modeling. That means you could model these processes in a different ways. You could model this longitudinal trajectory using the linear mixed model, and you can model this part, that means the time to event, completely different with the other things. You can directly use those longitudinal values as the predictor instead of considering the model. So this is called separate modeling. So if we do separate modeling versus joint modeling, how it differs? We are considering 5 different quantile level. So 25, 50 and 75 for each of the responses, and we consider these 5 different combinations which are sensible in some way, and we are computing the BIC and the DIC value. So Bayesian information criteria and deviance information criteria at each quantile level, both for the joint modeling and for the separate modeling. What we observe that at each quantile level, joint model provides a smaller value of BIC and DIC than the corresponding separate model. So it basically tells, so smaller be the value of BIC and DIC, better is your fit. So this tells you that your joint model is actually more appropriate for the particular data set that you have. Alright. So once we ensure that the joint model is the most appropriate model for this case, we go for the joint modeling, and I directly come to the result. So the first result that I show here is the quantile specific drug effect. Let's go to my model again. So in this particular model, first we want to see what is the effect of the medicine on the biomarker. This was one of our research goal, investigating the effect of the drugs on the longitudinal biomarker. I want to see what are these coefficients at different quantile level, and that will give me some thoughts. So this is the first plot. This plot is for the medicine 6MP, this is for the medicine MTX. Three different colors I am using for three different biomarkers: neutrophil count, platelet count, and lymphocyte count. So let us see the first plot. In the first plot, as you can see, so this particular plot means this is the mean value, estimated value, and these are the corresponding credible intervals. This is the length corresponding 95% Bayesian credible interval. So what we see, as long as 6MP is concerned, across all quantile levels, the effect of 6MP is negative for the lymphocyte count, which tells me that the 6MP always tries to reduce the lymphocyte count. 6MP is helpful in reducing the lymphocyte count. If you give a higher dose of 6MP, it will reduce the lymphocyte count, and it works very well. That means the value is the smallest when you have 25, 75, 75 level. That means the patient for which you have a higher level of neutrophil count and a higher level of platelet count, but a lower level of lymphocyte count. This particular combination, for them 6MP works the best. But anyway, across all quantile levels, it is reducing the lymphocyte count. As long as the neutrophil count is concerned, the red curve, the values are not that significant, more or less close to 0, credible interval contains 0, so we really cannot say anything. Same thing for the platelet, it is very close to 0, credible interval, except for this particular combination again, when you have higher neutrophil and higher platelet but lower lymphocyte, then only 6MP helps to increase the platelet count. Most of the other, and also in this case, otherwise it is more or less close to 0. What happens to MTX? MTX on the other hand is very helpful in increasing the neutrophil count. For the neutrophil count across all quantile levels, the coefficients are positive, credible interval does not contain 0. However, for the platelet count, it is not that significant. It does not help to increase the platelet count because it is mostly containing 0, credible interval. For the lymphocyte count, something interesting. For the lymphocyte count, it helps to reduce the lymphocyte count only when the lymphocyte count is at the higher quantile level, 50, 75, 75. So if the lymphocyte count is small, it does not help to do anything. If the lymphocyte count is at the higher level, it helps to reduce that. So this plot actually tells me that the quantile specific analysis is more meaningful in this context, because one particular medicine works for one specific group of patient which belongs to a specific quantile combination group. Next, we want to investigate what is happening for the quantile specific association. This comes from this particular model. How does three biomarkers associate with the relapse time? In other words, if I have a higher value of lymphocyte count, does it mean that my relapse times will be earlier? Let's see. So here what we see, again I have three different colors for three different biomarkers. Interestingly, we see that for the lymphocyte count, the coefficients are always positive, credible interval does not contain 0. That means a higher value of lymphocyte count, if you have a higher value of lymphocyte count, it will actually accelerate the hazard. That means you will have an immediate relapse. And that is well known because lymphocyte count is the key component of the leukemia. If you have a higher value of lymphocyte count, you will have an early relapse. However, the other two biomarker, platelet count and the ANC count, the estimates are always negative across all the quantile, credible interval does not contain 0. That means if you have a higher values of neutrophil count and platelet count, that will actually delay the relapse time. That means it's good for a patient to have higher values for platelet count and neutrophil count and a lower value of lymphocyte count if you really want to delay the relapse. This is exactly the same observation that we have from the exploratory data analysis. For the children for which we had a relapse, they had a higher value of lymphocyte and lower value of neutrophil and platelet count. and that is actually reflected after this thorough analysis. We exactly observe the same thing. Finally, we want to see, so this was our third question. Our third question was identify the time invariant covariates which have significant effects on the biomarker and the relapse time. This particular plot shows us significance of the fixed covariate. These are the different fixed covariate for three different biomarker: lymphocyte count, neutrophil count, platelet count, and the time to event, relapse time. Using three different colors, we are just distinguishing different covariates. If you have a red color, that means it has a positive effect. If you have a yellow color, no effect. Blue color, it has a negative effect. For example, as you can see, the gender for the lymphocyte count, it has a positive effect across all quantile except this level. Bulky disease for the neutrophil count always has a negative effect. Maybe age for the relapse time has no effect. So the interesting thing that we can observe from this plot is there is no covariate which is not important at any quantile level, and there is no covariate which is important for all quantile level and all responses. That means again a quantile specific analysis is important because some covariates might be important for specific quantile level but might not be that important for the other level. On the other hand, some covariates might have a positive effect on some level but a negative effect on the other level, and that is also interesting to see. So again it illustrates that a quantile specific analysis is really meaningful for the type of data that we have. One of the typical challenge in quantile regression model is what we say quantile crossing. Quantile crossing means by definition a quantile of order or quantile of level 75 should be higher than the quantile of level 50 or 25. Okay? So this is the definition of the quantile. However, when you are estimating quantile from the model, you do not have that restriction. So if it happens that your estimated quantile for a higher level is actually lower than your estimated quantile at the lower level, then your quantiles have no meaning. Estimated quantiles are meaningless. That is called quantile crossing. So your estimated quantiles should maintain the increasing pattern which is theoretically established for the quantile. So based on our estimates, we again plot the estimated quantile at the three level 25, 50 and 75 for all the three biomarkers. And what we see that we are actually getting the increasing pattern. That means our estimated quantiles are making sense and we do not come across any quantile cross, at least in our analysis. However, this doesn't guarantee that our method automatically prevents the quantile crossing. It's just we did not observe that for this particular case. There is no theoretical reason for which we should not have quantile cross in this case, and there are many literature which actually illustrates that quantile crossing is a typical problem in multivariate quantile regression model. So we also have the same problem, but at least for our case, our analysis, we did not have that. The final thing is the simulation study. We have to assess the statistical power of the proposed model, how efficient our model is. We perform a small simulation study for assessing the effectiveness of the proposed quantile regression joint model for non-Gaussian setting. So what we do, we just mimic the data set that we have. That means we simulate 3 longitudinal biomarkers for 200 subjects. For the first 10 time point, as if this is my treatment phase, and then we follow the subject for the next 15 time points as if they are my follow-up phase. So we observe the patient for the first 10 time points, follow them for the next 15 time points. We take 200 patients and we simulate 3 longitudinal biomarkers using the same model. However, for the random error, because you recall that in our model, this was basically the model for the longitudinal biomarker, and this epsilon ijk is the random error for which we consider asymmetric Laplace distribution in the context of quantile regression. We are considering 3 different distributions here for the random error. Asymmetric Laplace distributions with tau k equals to 0.25, this is a right skewed distribution. If we take tau k equals to 0.5 for all k equals to 1 to 3, that is a symmetric and heavy tailed distribution. It's a symmetric Laplace distribution, okay, double exponential. It's symmetric, but it's not normal, it has heavy tails. And in the third case, we simulate it from a standard normal distribution. So in the three different situations, first case I have a positively skewed or a right skewed distribution. Second case I have a symmetric distribution with heavy tails. In the third case I have a standard normal distribution. And I really want to see how my proposed quantile regression joint model works for these three different cases. We consider 100 replications of the data and we feed quantile regression joint model and the traditional linear mixed joint model. Linear mixed joint model means we model the mean function or the mean of the longitudinal trajectory, don't model them at the different quantile level. So that is called linear mixed joint model. So we are fitting both quantile regression joint model and the linear mixed joint model for all these three different cases. How do we evaluate or assess the predictive power of the model? This is called the discriminative capability of the model. In the joint modeling literature, the traditional measure or metric that people use is the area under the receiver operating characteristics curve or AUC. So let me explain what exactly AUC means in this context and how it has the discriminative capability. So first we define pi a t plus delta t given t. This means that I have a patient, ith patient. The ith patient was observed till time point t and we did not have any relapse. So I followed this patient up to time point t, small t, and I did not observe any relapse. And I observed the patient for the next delta t time point, so t plus delta t. So this is the probability that there is no relapse up to time t plus delta t, given that the subject was event free until time t. There is no relapse up to time t plus delta t. If I consider a pair of subject ij, where for the ith individual I observe a relapse in the time period t to t plus delta t. Up to time t there is no relapse. In the interval t to t plus delta t, there is a relapse for the ith patient, but there is no relapse for the jth patient. Remember, ti is the relapse time. So relapse time for the ith patient is some time in t to t plus delta t. For the jth patient, it is higher than t plus delta t. That means in the interval t to t plus delta t, I do not observe a relapse for the jth patient. If that happens, if you get such a pair that one you had a relapse, one you don't have a relapse, then your model should assign a higher non-relapse probability for the jth patient than the ith patient. If your model can do that, then your model has the good discriminative capability. It actually can discriminate a patient who has a higher relapse time than the patient who has a lower relapse time. So this particular probability, this is basically called area under the receiver operating characteristics, and we compute these AIC values for many different values of t. So this means that for an interval t to t plus delta t, if a relapse occur for the ith subject but the jth subject is event free, then the model must assign a higher non-relapse probability to the jth patient. Let's see what it is doing. So as I said, I consider three different distributions: a right skewed distribution, a symmetric distribution with heavy tails, and a standard normal distribution. I take t is 10, my delta t is 5, 8, 12. That means the interval 10 to 15, 10 to 18, 10 to 22. This is time interval. This is the true AIC value. True AIC value, since I am doing the simulations, I know the true AIC value. And this is the predicted AUC that I get from a QRJM model at the level 25, QRJM model at quantile level 50, and a linear mixed joint model. What we see here, as long as I have a positively skewed or right skewed distribution, my quantile regression joint model at the level 25 works the best. It dominates linear mixed model. If I take a symmetric heavy tail distribution, then the quantile regression joint model at the median level, it dominates. And if I have actual normal distribution, then linear mixed joint model is dominating, but QRGEM is not performing that bad. So they are comparable in some sense. So this basically tells that it's always safe to use QRGEM, because even if your actual distributions is normal, it is not performing that bad compared to the linear mixed joint model. However, linear mixed joint model fails to give you a good result if you really do not have a symmetric distribution. Okay? So this particular result actually illustrates that our model has a higher discriminative capability, and it can actually work well if you have a non-Gaussian distribution, and it always assigns a higher non-relapse probability to the patient for which you really observe the relapse after a long time. Okay, so that was basically the simulation. Here is the summary. So acute lymphocytic leukemia is the major cause of death among the children suffering from leukemia in the developing countries. Although I consider Indian data, I came to know that the similar case is happening for China also. The survival rate is really not that satisfactory, at least not 90%. Through the joint modeling, we can assess the quantile specific effect of the biomarkers on the relapse time, and that is really important to know. The overall mean regression curve doesn't give you much information. There are two limitations of our work. First of all, we assume an immediate effect of the drug on the observed biomarker. Once we have the model, if you can recall, we consider the effect of the medicine as if I take a medicine today and tomorrow I can see a direct change in the biomarker. But that typically might not happen. For some patients, it might take some time to get the effect. If I take a medicine today, maybe the effect can be observed after 2 weeks or 3 weeks. So that is called the lagged effect. We are not considering that lagged effect. We are just considering the immediate effect of the drug. If the drugs have lagged effect, it may be of interest to estimate the best lag. However, the lag also depends on the patient and specifically the genetic information of the patient. Depending on the genetic structure of the patient, the lag might differ from 1 week to 2 weeks to 3 weeks or maybe the immediate. So for this data, we did not have the genetic information as it is known that cancer is a genetic disease also. Okay, so it's really important to know the genetic information and also want to know what is the optimal lag for the medicine such that you can estimate the lagged effect. This is the acknowledgement. This work is basically a part of the thesis of one of my former PhD students in India, Dr. Shekhar Krishnan, who is a consultant oncologist of Tata Medical Center, and Dr. Manoj Gogoi, who is a clinical data scientist from Tata Medical Center. They actually performed this clinical trial and gave this data set for us to analyze. A paper based on this work has been accepted and published in Lifetime Data Analysis very recently. Thank you very much for your attention.
So is there any question? Okay, so maybe I have a very naive or general question because I'm not a statistic people. So I'm wondering what's the size of the data that you use for the simulation here, and how can you judge the quality of the data? I guess the modeling should predict the good result with a good data, but it may be influenced by if the data is limited, right?
Yeah. So as I said, for this particular study or in general when you have like cancer patient or schizophrenia patient, you don't expect that your data size will be very large. Okay, it's good if you don't have a large data because you should not have a large size. So my original data set, if you can see the original data set, we only had 236 children. Okay, so we mimic this data for the simulation study. We consider 200 subjects, but to getting back to your point, we really need large number of data. So although we take 200 subjects, but we consider 100 replications of the data. So it's actually 200 times 100. Those many data we are taking. Okay, one particular sample cannot have more than 200 or 300 data, but we consider 100 replications from this distribution, and we have 100 replicated data. Based on that, we are doing this inference. And that is the only way, because for this type of disease, you really cannot get millions of patients. So you have a small data, you have to keep replicating or simulating it from the underlying probability distribution to see the structure of the model. Yeah.
Okay. So is there any other question?
So I've noticed that this algorithm works very well for all symmetric data, and there's another type for all symmetric data, and there's would you be kind enough to share the PowerPoint on the, yes, QRJM for the 25 works well for a data for a skewed data, and I've noticed that it's very easy to like transplant it to other similar problems that have a small data set. So how do you expect that this might fit into a broader scope, such as like computer engineering or such applications, that we can use a different algorithm to distinguish skewed data and symmetric data, and then maybe transplant these methods to some more similar questions that might be solved?
Yes, that's a very good question. Actually, this question is the fundamental question behind quantile regression. So, as you pointed out, in computer science or in other kind of engineering field or in many different types of application, the goal is to find out the relationship between several variables. Okay, and regression is the tool for that. But the traditional mean regression model, when you use, your underlying assumption is that the probability distribution is symmetric, the normal distribution. But that doesn't happen in most of the time. So if you really have the skewed distribution, or if you really have left skewed or right skewed or any type of skewness if you have, first thing you do, you try to transform the data. But even after transforming the data, if you do not get the symmetry, then you have to go for the quantile regression. So quantile regression is the robust method because it does not depend on the normality of the distribution. So no matter what type of skewness you have, if you do a quantile regression approach, that's why quantile regression is so popular and so robust, that you really do not need a symmetry, you really do not need normality in your data. For any type of data that you can have, you can always perform a quantile regression, and even if your actual data is symmetric, quantile regression will be as good as your usual regression. So my recommendation will be, it's always safer to use the quantile regression than the traditional mean regression model. That's all.
Okay, so is there any other question? Okay, so if there's no other question, let us thank our speaker again.
Thank you so much.
Okay, so the next talk is starts at 10:30. So we have about 14 minutes.